Okay, I shall start in exactly, I don't know, 10 seconds. All right, this is a bit awkward because, oh, whatever. Okay, I'll just start. Okay, so, um, in terms of what will come tomorrow, obviously I cannot say exactly what, but the thing is, Half-Life is definitely going to show up one way or another. So the only two things you have to know for Half-Life is one of them could be a graph. So if my camera resolution is not that good, oh well, blame Samsung. So you always have time on the x-axis. You guys have to know this. And then you have activity on your Y. Yeah, don't worry about the units that much. It doesn't really matter. But you have activity against time. Now, the thing is, Half-Life graphs are always exponential. So they just always have a curve like that. They'll give it to you in the question if they do give you this. And then you have to derive, or you have to find what the half-life is from this graph. So, for instance, let's say that you start off with, and they'll give you this in the question, by the way. They might tell you that activity initially is 100,000. All you guys do is just find half of it, which is, whoops, okay, I kind of set myself up there. But it's half of it will be 50,000. And then what you guys do is you go to the initial activity, which is 100,000, go all the way down, go for 50 as well, go all the way down, and then you just subtract the time between them. So let's say at 100,000 activity, your time was 50 seconds, and then at 50,000, your time was 100 seconds. The difference will just be 50 seconds because that's what you just take them away. But that's pretty easy, and that's besides the point. I already showed you guys that. The real deal is pretty much if you have this. So say you start off with 5,000 BQ. So this is your initial activity. They could really mess you up, and they can tell you what is the activity after three half-lives. So let's say after three half-lives, what is your activity? So you guys should be writing this down at the same time like me. So what you guys do is you start with 5,000. You just half it three times. So you go 2,500. Half of that is 1,250. And then the third one will be, okay, I'm a bit stuck here. 675. Nope, 65. Yeah, is that. So as you guys can see, one half-life, two half-life, three half-life. So that's the second most difficult question they can give you. I hope that makes sense. If not, just comment because I'm using my mobile. I cannot really see what you guys are saying unless you type it. So one, two, three. Now, the worst thing I've ever seen in all my years is this. They'll tell you um, um, after how many half-lives, after how many half-lives do you get, and it'll give you a fraction. Maybe let's say 1 out of 32 of the activity, right? Now you're probably thinking, what the hell is going on? It's not that bad. What you guys are meant to do is, once again, you start with the initial activity, which is 5,000. And then think about it like this, guys. First, you're going to divide it by half. So the first half-life, you half it. Then the second half-life, you quarter it. You keep dividing by two. Then what should it be? 1/8. If you can see that. 2 and then 4, because 2 times 2 is 4. 4 times 2 is 8. The fourth half-life should be 8 times 2, which is 16. And then the fifth half-life is 1 over 32. So this is the absolute worst question they can give you. You can't get any harder than this. So once again, the question said, after how many half-lives do you get 1 out of 32 of the activity? We started with 5,000. What you do is you find the fraction. So it's half, quarter, 1/8, 1/16, 32. That's 5 half-lives. So you need to half it 5 times. So if you half it 5 times, you basically get first half-life is 2,500. Second one is 1,250. Third one is 625. Fourth one is 312.5 roughly. So 1, 2, 3, 4. And then the fifth one will be half of that, which I cannot bother to calculate. I think it's roughly about that. I'm not too sure, yeah. So you just half it, what's it, 5 times. 1, 2, 3, 4, 5. All right, try this one, guys. I'll give you a second. So try this. Initial activity. By the way, if you guys can answer all these questions, you're pretty much going to get grade 8 tomorrow, guaranteed. So initial activity is 16,000. Find activity. Oh, what should I say? 6 Half-Lives? Or I'll give you 30 seconds or whatever. Just try it. So half is 6 times and give me the answer. Whoever gets it first, just comment. Well, I do it off screen, I guess. Okay, Billy done it a bit too fast. I still haven't completed it yet. Oh well. 1, 2, 3, 4. Wait, 1, 2, 3. Yeah, you guys got it. Well done. Yeah. So the activity after 6 Half-Lives is 250 because all you do is you do 16,000 and then you just go down, what's it, 6 times. So it'll be 8,000, 4,000, 2,000, 1,000, and then 500. And then after you have 250. Yeah. So if you guys look here, it's basically 1, 2, 3, 4, 5, 6. There you guys go. All right, so that's pretty much that. Okay, so is everyone okay with Half-Life? Because this is the absolute worst you can get. If you guys are, then we can move on, I guess. I'm only focused on relevant stuff, so meh. All right, next thing is, let me think. Yeah, I guess states of matter. Let's do this in like 2 minutes or whatever. All right, so um, leave my man Billy alone. Come on, guys. So states of matter. So say you have solids, liquids, and what's it, gases. All right. So what they might ask you in the exam is they might ask you um different properties of these three. So I'm just going to quickly go through it quickly. So you see solids. Basically, what you guys need to know is that solids are they have particles in fixed positions. You guys can write this down because I'm definitely not sending this. Particles in fixed positions. And you can draw it as well because if you're a visual learner, it's probably easier that way. So you guys should know this from chemistry, but all the particles are pretty much touching. If even one of them is not touching, you will get 0 marks for it. Just be warned. So all of them should be touching. And then, yeah, so you get this. So particles in fixed position, and then they vibrate in a lattice, I guess you can say that. All right, for liquids, no, please don't. All right, so particles, fixed positions, vibrate in a lattice. Liquids, they have the ability to flow. And liquids also, they have a fixed volume, right? Now, I can give you guys an example. Say you have a can of 7-Up, which is 330 milliliters. If you poured this 330 milliliters of liquid inside a giant jar, 1 liter jar, it will still only have a volume of 330, as in it will not expand magically. So liquids, they have a fixed volume, but they do not have a fixed shape. So no fixed shape, basically. Why is my brightness so dim? Wait 1 sec. Yeah, apologies for the vibration. I'm using my phone. I don't really have a camcorder, so Pokemon, huh? All right, and then gases is probably the most important. They will ask you one of these three tomorrow, by the way, either this, or this. So whichever one comes up, there you go. So gases, they move at random speeds. So the particles move at random speeds. Well, I guess I should say different speeds as well. So every single particle in a gas, if I was to draw it right now, this just shows the effect of them moving. But every single particle in the gas is moving in a different direction, and it's very random as well. You can never predict where any one of these will go. So you need to say they move at random, and they all have different speeds. So they move, yeah, different speeds. So that's what you guys need to know for states of matter. In terms of physics, nah, because they asked in chemistry, so they won't ask in physics anymore. But these three, they will definitely ask you, or they might try to bring it up in a multiple choice or whatever. But you guys have to understand it, yeah. All right, so I'm gonna move on. Next thing's next. Let me think. What's most likely to come up? All right, let's just do electricity because if you don't do electricity right now, it's not one of those topics you can do last minute. So write these three formula, and we're just gonna keep doing loads and loads of questions until you guys pretty much master them. So P is equal to V times I. P is equal to I squared times R. And you have to memorize these, by the way. If you can't catch up, too bad. So P equals, yeah, VI, I squared times R. And then you have Ohm's law here as well. Yeah, so I'll let you, I might give you guys, I don't know. I might as well give you 10 seconds or so. Yeah, by the way, sorry, I cannot see the comments half the time. So, yeah. All right. So you have these three. Let's start questions. So let's say the question tells you voltage is 30 volts and current is 0.05 amps, right? What would the power be for this question? This should be super easy. You should get it in like 10 seconds using one of these formulae. Okay, so in case no one got it yet, it's just you just use this first formula there. Because look, in physics, you lay out all the information like this. You have power, you have current, you want to find power. Yeah, sorry, you have voltage and current, you want to find power, so you just times them. Yeah, so Penny's right. So it's 1.5, but she didn't put the units, so that's wrong. Nah, just kidding. So 1.5, and then the units is watts, W. Yeah, so that's all you do. How about if I gave you this? If I said current is 2 amps and volt no, I shouldn't give voltage. Resistance is 0.45 ohms. What would the power be then? So you have this information right now. Just look at all the formulas. We can't use the first one because you don't have V or you don't have V there, as you can't use it. That's a no-brainer. And then the second one, you're looking for power. You do have current and you do have resistance. So it'll be 2 squared multiplied by 0.45, which is 4 times 0.45, which I believe, based on my very accurate calculations, is 1.4, is it? Oh, is it 1.5? Oh, okay. 1.6 rather, no? Oh, whoops, 1.8. Yeah, that's right. Okay, so 1.8 watts. That's what you guys do. All right, let's work backwards now. Let's say they've given you the power to be 1,800 watts. Oh, welcome, Casey. All right, so let's say you got power, and then say they give you the current is 0.5 amps. What is the resistance? Try this one. So you guys have to work backwards now using formula number 2. In your exam, just pretty much lay out everything like this. It should be fine. So power, current, resistance. You're trying to look for this, you know that. So, okay, let me go through it. So to find the resistance, I just lay out my formula as usual, like this, and then just rearrange. So R is pretty much, well, okay. Let's see, P over I squared. All right, you said 900. Let's see. So you done 1,800 divided by 0.5 squared, which is the same as 0.25, I believe, is it? No, wait. Yeah, I think so, yeah. And then this is pretty much 7,200. Am I correct or am I correct? I think it should be right because dividing by 0.25 is the same as multiplying by 4. Okay, so that's how you do that, yeah? Okay, that's good. So I hope everyone's okay with this, yeah? Oh, you didn't see the squared. Okay, yeah. In the exam, if you guys forget this formula, you're pretty much done for because they haven't brought this for the last, I don't know, I don't know, maybe I don't want to make up stuff, but it hasn't been here for ages. So if this comes up, it's going to be like a heavyweight question. Just make sure you memorize these two if you're going to memorize any two formulas in this exam. Make sure you memorize these two. Wait, nope, Frankie, because there's a squared, remember? There's I squared. So if your current 0.5, you need to put 0.5 and then square it. Circuits is all right. I mean, the things that you guys do not like are the things which are least likely to come up, so it's fine. Yeah, the graphs will definitely come up, so you can't escape. One of them will come up for sure. So, no, don't worry, it's very wrong. What? Okay, so I hope that's fine. Now, let me give you the worst, the square. Okay, let me do one last question for electricity, or at least for calculations, because I'm trying to prep you for the worst. They've given this in introductory AS, but I think it might come up. So once again, you have your formula here. Say they basically, and there's a fourth formula, Q equals IT. Now the thing is, Q is equal to charge. I'm not too sure, Billy, for triple. It's been ages since I taught it, but it's P1 to 7 for combined. I think that should be it, no? Okay, so let's say they give you a question like this. They tell you charge is equal to 3 coulombs. They tell you time is 40 seconds. And then they tell you voltage is 500 volts. And they tell you to find the power. So try this. This could be like a 6 marker. I'm just making up stuff, but this is probably the worst thing I could think of. So try this. You might have to combine more than one formula. So once again, you have Q, you have T, you have V, you have and you're trying to look for P. So out of all these formulas, so if you got formula 1, 2, 3, and 4, which one of them? Well, you have to use more than one anyway. So let's start off with the first formula because you have both Q and T, so you can find I. So what we do right now is we rearrange this formula right now because we are trying to look for I. So if Q is equal to IT, and we're trying to look for I therefore has to be Q divided by T. So if you do Q divided by T, that gives you 3 divided by 4T. I wish I didn't choose these numbers, but let me see. That should give you... what should I give you? 3 divided... Is that like 0.075 or whatever? I'm not so sure. I think it gives you this, just a guess. 0.075. Because yeah, 300 divided by 4 gives you. So it gives you this. Now because we have current, guys, we're one step closer to finding power because if we have current and we have voltage, then can we not use this formula here if you guys think about it? Can we not use this here? Equation number 1. Because you have voltage and we just calculated current now. So all we do is just multiply them together. So you get voltage, which is 500, multiplied by current, which is 0.075. And I have absolutely no idea what this gives us, but I shall just wait for someone to write the answer. I think it should be 7.5, 3.75. Not too sure. Oh, it's 37. Yeah, 37.5. And watts. So this might be like a 6 mark in the exam, just because of how hard this is. You have to use more than one formula, and because you have to use more than one formula, you have to memorize both. You will definitely get 6 marks for this. So just in case it comes up, I hope it makes sense. Once again, you try to look for power. Just look at both the power formulae. In the beginning, we did not have enough information, so you had to find current from these two, which we did there. And then from current, you multiply by voltage, and you get the power. All right, so I hope that's good. What next, though? It's like I'm trying to prophesy what's going to come up. Yeah, I'm kind of lost right now. All right, let's say you are going to look for... Are you guys okay with the radiation? No, actually, we just done that. Scratch that. Once again, profile. I'll do this 2 seconds quickly. Oh yeah, actually, yeah, I can the formally I think I sent it to you, Casey. I sent it to you guys. There's a whole list of formula you guys have to memorize. Well, I'll write them here anyway. So this is everything you guys have to memorize. Kinetic energy is half times mass times velocity squared. GPE. Yeah, I think radiation is fine. We're just gonna move on to something new. I think we're gonna move on to let me think. Pressure and temperature and volume, yeah, because that one we haven't done. KE, GP, what else is there? So this is for energy. And then for density, you have to memorize the formula as well. So mass is equal to volume times density. Yeah, so one, two, three, you guys have to know that. Yeah, radiation's easy. So you have these three, and then also you have electricity ones, which I just showed you now. P is equal to VI. Out of all these formulas, make sure you memorize these electricity ones, or you are a dead man or woman walking. So PP, then what do you have? Ohm's law, V equals IR. Yeah, so I think these are the main ones you have to memorize for tomorrow. Okay, so what we're gonna do is I'm just going to show you the IV graph super quick, and then if you guys can just let me know what you want in the comments. But I'm gonna move on to gas pressure just because that's quite hard. So once again, what symbol is this? If you guys can just comment. Whoever gets it first gets a sweet, I guess, but you know. Bulb, okay. Yeah, I guess Casey got it right. Yeah, he took the shortcut and wrote a four-letter word, but it works anyway. So for filament lamp, you kind of a weird S like this. Yeah, Casey got it. Get in there, son. All right, so you have this right now. So you guys have to memorize this curve for tomorrow. And then let's move on to the next one. Let's say, what's this device there? Oh, the thing is, Billy, because yeah, Casey got it again. But the reason why this is not what's it called? Proportional is because inside the lamp itself. So look here. So as your voltage increases, it increases your currents. But we know that in a metal, if your current increases, it heats the metal up, and then the resistance goes up, therefore kind of curves. So the resistance is not constant for a filament lamp. That's why. All right. So Casey got it. So for fixed resistor, it's just nice and linear like that. Let's do the third one, which is a not rather not say it. All right. What is this one? Let's see if Casey can get a hat trick. Oh, never mind. Okay, Penny got it. Good one. Yeah, nice one. All right, so yeah, it's a diode. So for a diode, it only allows. Yeah, Frankie, I don't know. Wow. Okay, 3 minutes behind. So it kind of goes like this. So you have it's on zero right there, and then it kind of goes up like this. Guys, you gotta. Yeah, I don't know who your internet provider is, guys, but yeah. So this one goes up like this. A diode pretty much is on the negative side is zero, and then it just rises on the positive side like that. So what I would suggest for all of you guys several times tonight, just start copying these several over and over and over and over again. You will not be disappointed, yeah. All right, so you got one, two, three. Now that we're done with this, I'll leave it one last for another 10 seconds, and then we'll move on. Otherwise, we won't make it. I don't think there's that much content in physics compared to the other two. It's very, very basic. It might be hard, but it's just very basic. It's the same thing over and over. All right, so once again, filament lamp, resistor, diode. Moving on. Now, what you guys need to understand next is I'll just do two mega questions that could come up in electricity. They do not involve numbers. They involve the 6 markers we have to write stuff. So let's say you have a resistor here, fixed resistor, and then say you have a thermistor here. I'll explain what thermistor is as well in a sec. So you can draw this graph as the circuit as well. Very easy circuit. You just have a battery, resistor, thermistor. A thermistor, as the name suggests, is a resistor that depends on the heat. So, or it varies with temperature. So, but it's the opposite. So, a thermistor is resistor which depends on temperature. So it's just that simple. But the thing is, in the exam, you guys need to know two things. It's negative. So if your temperature, I'll use T for temperature, but I write temp like that. If your temperature rises, your resistance does the opposite, it drops. And if your temperature drops, your resistance rises. So you guys have to know these two. You might want to write them down. Yeah, it's just the exact opposite. When it's very hot, your resistance drops. When it's very cold, your resistance increases. Now, what I want you guys to understand is they might ask you what happens to the resistance when the temperature drops, so you can just say it rises. But alternatively, they could tell you what happens to the share of voltage. So just to give you guys some context, say you have 20 volts there, right? Say the resistance initially is equal 500 and 500. What you guys need to understand is voltage is shared between different devices in a series circuit. So if you got one loop like this, your voltage splits between them equally because the resistance is equal. So each one of these will get 10 volts there, and then we'll get 10 volts there. That's what you guys have to understand. This is like super important. Yeah. So as long as the resistance is the same, they both get the same voltage. What would happen though? Let's now say there's let's say hypothetically the thermistor pretty much let's say the temperature gets really hot right now, right? So if the temperature gets really hot, we know that the resistance is going to drop. The resistance of the thermistor is going to drop. So if the resistance was 500 before, let's just give it any value now. Let's say it dropped to like 200, right? And because it dropped to 200, and this is still 500 because it's fixed, what we can now say is that this will get a bigger share of the voltage than that. Whatever has more resistance gets a bigger share of the voltage. That's pretty much what you guys need to know. So more resistance requires more voltage. You guys have to know this for tomorrow. Yeah. So if you compare these two, this is only 200, this is 500. Because this is 500, it'll eat up more voltage because it's harder to get stuff through it. Whereas this one will use up less. So they might ask you that. Simple as this. It could be a 6 marker. They give you this first, then they give you that. Then it's a compare what happens. All you say is that the resistance of the thermistor dropped because the temperature went up, and then therefore it uses a smaller share of the voltage and more goes to the resistor. That's it. Does it make sense? Just give me some feedback. Okay, that's good. All right, good, good, good. These are all the hardest stuff. I'm not doing the easiest stuff because they carry 1 mark. Who wants 1 mark? All right. Let's see. Next thing, let's deal with insulation because even though it seems easy, everyone loses easy marks in it, I guess. So, all right. So you have a house here. What are you joking? Wait, let me see. Okay. So you have a house here. Now they're asking in the exam which one pretty much which one of the features helps, I guess, reduce energy loss. So let's start with the door. What you can do to the door is basically you just put draft. I think that's how you spell it. Draft proofing underneath the door, right? That's all you do. And that minimizes the amount of energy loss. But I doubt they'll ask you that. What they usually love asking is either the walls or they ask you the roof. It's always one of these two. Or maybe the windows, but they ask that every other year, so I highly doubt it. So just write these three. So these three are the things we're going to be looking at very quickly. And if you know them, then we can just move on very easily. All right, so your windows, what you guys need to know is if we draw them from a cross section, so double glazed for a reason. So you have, let's say this is inside the house, and then this outside the house. And what you guys need to know is that energy or heat energy always wants to go from where there's hot to cold. So ideally, the heat waves will want to pretty much escape like that. But to prevent that from happening, we have two pieces of glass, and between them we have some air, right? Now the thing is with air, all you guys need to mention in the exam is double glazing. I'll tell you guys what to write. So double glazing has, what can we say? Air between the two layers of glass. And what you guys need to mention is, so that's the first thing. So double glazing has air between the two layers of glass. Second mark, you can basically say that air absorbs radiation. So basically, instead of the waves going all the way outside, at least they go absorbed there and they stay put there rather than going all the way outside, yeah? So your house temperature will not reduce that much. All right, so yeah, so air absorbs radiation. That's pretty much, it's pretty easy. I think the worst thing is when they ask you about the roof or the walls. So I'm gonna move. I'm very sorry if you guys haven't finished, but I'll leave it like that, I guess. Actually, yeah. Nope, never mind, wrong way. So what you guys can look at now is let's look at the walls. So the walls, how they reduce, whoops. All right, I'll go back to the house. Actually, I can just write down here, right? Yeah. So what you guys need to know is that the walls, they have wall cavities. Yeah, insulation, yeah. So they have wall cavities. So they also have pockets of air to trap radiation, or we can say rather to absorb radiation. So that's the first thing. And then after that, what you guys need to know is that they also have shiny material. So you guys think about it like this, right? If you guys have a car, or whatever looks like a car, I guess, but you see, when it's very, very hot, what happens is you can put some very, very reflective, let me think, you can put some very, very reflective foil on the windows of the car to prevent the car from getting too hot. Let me just fetch it up quickly and I'll show you guys one sec. Okay, I cannot seem to word that. One sec, guys. Just give me 1 second. All right, here we go. Let me just move this quick. Look here. So it's kind of like this. Yeah. So this is pretty much like some reflective material. So when the light hits the car, instead of getting absorbed, it bounces back because it's reflective. So the walls pretty much have the same thing. If that makes sense. Yeah. All right. So what you need to mention is reflective material. Not exactly foil, but it's like it's made from like aluminium or other reflective material. Pretty much. So reflective material to reflect radiation so that it doesn't escape. Yeah, so once again, radiation wants to always escape the house because outside is colder. But what happens is the shiny material will basically, when the wave's trying to escape, it bounces back. Yeah, so it kind of causes it to reflect. That's all you guys need to know. Yeah, so wall cavities, aka pockets of air to absorb radiation, and then reflective material to reflect radiation as well. Okay, let me think. Nuclear equations? No, I don't think so. Okay, let's move on to gas pressure because they might ask you this as well. What you guys need to understand is, say you have a deodorant can here and it has gas particles inside it, right? Nuclear equations are like alpha, beta, gamma when something decays, which I can show towards the end, but it's very easy anyway. So let's just do gas pressure and temperature quickly. Yeah, so you have a deodorant can. Let's say someone leaves it for whatever reason at 50 degrees Celsius. As you said, yeah. So it causes so they might ask you to explain what happens. First thing you need to mention is particles gain kinetic energy. Because think about it, guys. When something gets hotter, it's more energetic, so it gains kinetic energy. If you have more kinetic energy, they move faster. This gives you a second mark. Third mark, you need to mention that more frequent collisions. So because they move faster and more haphazardly, they collide with the walls more often. So more. Oh, this is why I hate writing on the left hand because when I write, you guys can't see. But anyway, more frequent collisions. Oh, red shift and blue shift. Oh yeah, I can do that towards the end there. That's fine. So more frequent collisions, move faster, particles gain kinetic energy. Eventually, what can you guys say? Eventually, pressure increases. And think about it like this, guys. Because it moves a lot more and it hits, there's way more collisions. Eventually, it can't withstand the pressure and it just bursts. So, uh, canister will burst due to pressure. There you go. Yeah. So if this is like 6 marks, it's very easy to answer it. That's all you guys need to mention. Even though people don't necessarily like this topic, but oh well. Okay. So nuclear equations. I'll just do one or two quickly. Let's say you have uranium 238 and then 92 there, and they tell you it undergoes alpha decay. By the way, you guys have to know these symbols. This is alpha, this is beta decay, and this is gamma decay. No, there's no gamma decay. Sorry, whoops, what am I saying? All right, so alpha decay and beta decay. What you guys need to know is, say they told you that this uranium's undergoing alpha decay. What happens is alpha is the same as a helium nucleus. So you guys have to know in the exam that alpha is the same as this. You just have to memorize. So this is the same as alpha. You guys have to know that beta is the same as an electron, which is pretty much like this. And gamma is the easiest. Gamma just has no mass. Gamma is just 0, 0. This is a wave, yeah? So you guys have to know this for exam. Memorize them. So alpha is the helium nucleus, beta is an electron, and then gamma is, what's it? Just a wave, electromagnetic wave. So if uranium undergoes alpha decay, alpha is 4 and 2, so you just place 4 and 2 there. And then you're going to get a new nucleus, sorry, because you start with something very heavy. It wants to become lighter. So this is super heavy right now. To become lighter, it chucks out alpha, which has some mass. So obviously the remainder of it will be a bit lighter than it started with before. Yeah, so all you do is subtract though. It's 238 minus 4 is 234. And then 92 take away 2 is 90. And then whatever. This is not chemistry. This is not the inferior science. We don't need to know what the actual symbols are. They gave it to you in physics. So all I done, 238 minus 4 is 234. 92 take away 2 is 90. That's pretty much it. Let me show you how to do beta quickly. Uranium once again, 238, 92. No, that's fine. That's fine. And then, so the thing is with beta, you have 0 minus 1. And you're trying to find the new numbers. So once again, take away 238 minus 0 is 238. This is a bit tricky. 92 minus minus 1. Everyone gets confused about this, but minus and minus, you guys should know, is the same as positive. So it'll actually be 93. Yeah, so 92, take away 1, which is this. And then forget about the element. It doesn't really matter. Does that kind of make sense, folks? I feel like I'm forgetting something. I don't know what it is, but I think there's a topic. Wait, radioactivity, maybe energy. I think, yeah. All right, that makes sense. Yeah, let's go. Let's go to energy because energy, I feel like I have not touched it whatsoever in terms of energy sources. So energy stores, I guess. However, AQA say it right now, yeah. So you see, with energy, you guys need to know that you have kinetic. Just try to write as many as you can. The more you can write, the better. So try writing them ahead of me as well. Chemical, gravitational, potential. What else is there? Thermal. Nuclear. What else? 1, 2, 3, 4, 5. Oh, okay, that's pretty good. Elastic potential. Okay. So we'll go through a bit more afterwards, but I just want you guys just to focus on this. So based on this, yeah, thanks, Billy. That's pretty good. So they might give you a question where you have an airplane. So you have an airplane and they might tell you what's the energy transfers that's going on. So think about it like this, guys, right? Chemical energy, I think there's a misconception with chemical energy. Chemical energy is pretty much found in fuels. So think about it. What's the fuel for humans? It's found in food. What's the fuel for a car? Is petrol or diesel. And then for handheld devices, batteries. So you guys have to know that chemical energy is stored in these pretty much, yeah? So in a plane, obviously you need petrol for that. So what do you start with? You start with chemical energy, because they could give you a 3 mark on this. Chemical energy, then think about it. The plane's going to start to move. So that's what? Kinetic energy to the kinetic energy store. And then what happens is it takes off eventually. So that's going to be gravitational potential energy as well. But then obviously you have to know there's some wasted. If you think about it, there's sound and there's heat as well, a lot. So you are wasting some energy, but these are the useful ones if you think about it. Whereas these two are kind of wasted. So I hope that makes sense. I want you guys to try this one now. So say you basically have, they might give you, because they like doing it between two different systems. So they might give you some logs, wooden logs like that. So this is just wood. And then you basically light it up, yeah? So lighting up some wood. Now the thing is, we know that wood is a fuel because it has chemical energy as well as fuel. So what we need to say you're trying to heat up some water, like a stove of water. So what you guys need to know is that when you light the match or whatever and you activate this, you're gonna use chemical energy from the log, or let's say from wood. So you start with chemical energy from the wood, and then that gets transferred to the thermal energy store of the water. Because think about it, when there's fire, so to speak, there, it's basically just radiating energy and it's going to the water and it raises the temperature of the water. So thermal energy store of the water, pretty much. Seems pretty straightforward, but you won't believe how many people get this wrong in the exam. So they could give you anything. I'll give you one last one. They might give you like a roller coaster, and then they might tell you what is the max, which point there. I'll give you like A, B, C. They might tell you where is GPE the max at. And we know that GPE increases with height. We know this is the highest point. So this is max GPE, or max gravitational potential energy. They might say, where's the maximum kinetic energy? We know it's going to be there, because think about it. When your cart is going down, the further down it goes, the faster it gets. So that's going to be the fastest point. So you're going to have max kinetic energy there as well. So I think all in all, you guys have to know at least a few types of energy. I would say mainly chemical and what kind of stuff store chemical energy. But then guys should be good. All right, yeah, let's do efficiency, I guess. Let me know if I'm going too fast, but then again, time's against us. So you see efficiency. What's P8? I lost track of what the topic names are, but oh, the thing is, because point C, where the hell did it go? Oh, here we go. Because point C is in between. Like it almost has max GP, but still not as high as that. So it's not really relevant. They don't want you to mention every single point. In the question, they only will ask you maybe where is the max GPE or the max KE. So these are the only two significant points. This is just somewhere in the middle. It's like almost max GPE. Yeah, so it's not one extreme or the other. These are the only two extremes, yeah? Because what they could do, they can give you like loads of random points like that. But all of these ones don't really, they're not that relevant because they're not all the way at the bottom or all the way at the top. So there you go. Efficiency is pretty, it's not that bad. Let's say that you always have input energy. You guys need to know this. So you have input energy. So this is the total energy that goes into something. Then what you have from that is you have useful output. And then you have wasted pretty much. Now, I've seen some people give the most bizarre answers in the world. Some people thought input plus wasted gives you useful. I don't know what world how that's possible, but make sure that you guys know these two together. When you add them, it gives you this pretty much, which kind of makes sense because you're feeding all this energy to a system. Some of it will be put to use and some of it will be wasted. Now, let's put it into context. Say that maybe you have 20,000 joules of energy, of input energy, and they might tell you 8,000 joules is wasted. Now, this is going to be pretty easy. If this much is wasted, how much is useful? All you do is subtract them from each other. So that will give you 12,000 joules, which is useful. But they won't give you that in exam. They'll ask you for the efficiency. The formula for efficiency, and you have to memorize this, is... did I forget it myself? No. It is useful energy over input energy multiplied by 100. So if you guys look here, your useful energy is 12,000. Your input energy is how much? 20,000. And then times it by 100. If you do the maths, that should be 60%. So 60% efficient. What that means is for whatever energy it gets, 40% is always wasted and 60% is put to good use. That's all it means. Yeah, so try this one quickly. I'll let you guys try one. Otherwise, no point just watching for physics. Say that your input, give you a weird number, 17,800 joules. Wasted is 7,800 joules. Fine efficiency, I guess. All right, try to do this under 30 seconds. Go. All right, 10 seconds left. Okay, so let me just go on with it. So what we do is, anyone find the answer yet? No? Okay, never mind. I'll go through the answer. So the formula once again was what? Useful energy over total energy or input energy. And then you multiply by 100. So if you're useful, you don't know what you're useful, you need to subtract these two away. You get 10,000. And then you divide it by your input or your total, which is that much. And then you're going to multiply by 100. And I have no idea what this gives you. If I have to roughly estimate it, okay, never mind. Thanks, Tegan. So it's 56.1%. Yeah, so there you go. So that's how you do this kind of question. It's not that hard. I mean, they could reverse it. So they could actually maybe tell you your input was 8,000 joules, and then they can tell you efficiency was 60%, and then they could tell you find the useful. So you have to work backwards. They could, in fact, do this. All you guys do is just the same thing. Write out the formula again. So useful over input multiplied by 100 equals efficiency, right? All you do is just plug and play. So useful, we don't know what it is, so just leave it as X. You get, and then input, how much is it input? It's 8,000 multiplied by 100, and then is equal to efficiency, which is 60. And then all you guys do is do inverse operation. So if this is multiplied, then you're going to get rid of it, divide it by the other side. So you're going to divide this by 100, divide that by 100 to get rid of it. So it'll be like X over 8,000 is equal to 0.6, because when you divide this by 100, and then you just cross multiply. I don't know if your math teachers taught you this divisive method, but all you guys do is you just cross multiply like that. This by that, and then this by that. So X times 1 is just X. And then 0.6 times 8,000 gives you a number which I believe is 4,800. Yeah, so I mean it kind of helps to know how to rearrange your maths. Otherwise, you will kind of struggle. But I doubt that's gonna come up if I'll be honest tomorrow. Yeah, just memorize the formula though. Memorize useful over total multiply by 100 gives you the efficiency. At least you should know that much. Okay. I can do. Let me think. It's probably best if you guys suggest a topic for me to do, because I, I mean that I think you guys are okay with the practicals, the Eureka can, and the what other ones are there? Things the red shift and blue shift. Gulp. Okay, let's do this. Red shift and blue shift. So minors. Oh, are you talking about radioactivity? Oh, I hate stuff. Wait, what? So I used Oh, Chicardi, the thing is that you don't have to do C for the roller coaster. As in only points A and B were significant. C was not an important let's see. Red shift and blue shift is triple. Yeah, I think what's probably best is let's just finish all the combined stuff first because it's in I guess it's in everyone's benefit and then can do triple. But for combined, is there anything else though? Oh, Isabella said practicals. Well, I mean, it's no secret that you guys know that either it'll be Eureka Can practical tomorrow or it'll be specific heat capacity practical, which that's a bit too common, so don't count on it. This one hasn't come in ages, so Eureka Can, SHC. I'll put a star because it's quite important. And then you have resistance versus length of a wire. This is an electricity one, which is quite important as well. And then you have Ohm's law. Yeah, Eureka Can is pretty much in both. Yeah, it's not only in triples, is in all of them. It's this one. If I was to do it, it's pretty much you have like a rock like this, and you want to find the density of the rock. So that's what you want to do. You want to find the density of something in regular. So you can't use length times width times height because it's in regular. So what you do is I write the steps for everyone. What you do is we know density is equal to mass over volume. Okay, yeah, sure thing. So first you write the formula. So you measure mass using a mass balance. If you already know this, it's just good practice for you to write it again without looking, I guess. So measure mass using a mass balance. Yeah, pretty much, Billy, yeah. Then what you do is you place object gently in water or in Eureka Can. Object gently, what's it? In a Eureka Can. And then, okay, I don't know why. One, two, three. Yeah, so what you guys need to know is that basically when you place in the Eureka Can, if I was to draw it, let's say you got water there, the spout there. When you place this object with a string gently inside, it's going to cause some water to overflow. So you collect that water in a measuring cylinder, and the volume of that water is very important. So the volume of water displaced equals volume of irregular object. This is super important. If you can't answer this, you can't do it. So volume of water displaced from the Eureka Can. This is called Eureka Can, by the way. All right, is equal to volume of a regular object. And there you guys go. But then what you guys need to mention is they don't give you 6 marks just for saying this. You need to then use the formula, but also you need to mention that you can let me think. Yeah, you have to use a string. So you attach a string to the object and then you place it in gently. Because imagine you just throw it with your hand, it's gonna cause a big splash. You're gonna lose some water there, and it's not necessarily that accurate. I mean that reliable, is it? So you use a string to place object gently. You get 1 mark for saying that. Oh, the only formula is this one there. Is density equals mass over volume. That's the only formula you have to use. For yeah, the thing is for safety, there's not much to say with safety in all honesty. I mean, there's not much really. They don't give you marks for talking about safety in this question. They give you marks for talking about how you can make it more reliable. Not you can talk about accuracy as well. Accuracy is basically when you use devices that allow you to get better or more precise readings. So if you use a more sensitive mass balance, if you use a measuring cylinder. So like basically, I can give you guys a scenario. Say you have two cylinders, one that has increments like that and another one that has increments like this, right? We all know this one will produce more accurate results because it has more increments. Yeah, so you just need to mention stuff like that. So use a measuring cylinder that has more increments, which will give more accurate readings, as opposed to a beaker, which we all know has like one, two, three, which is pretty terrible. Yeah. So don't get confused between accuracy and reliability because if I was to write the difference between them, let me know if you want me to go back. But yeah, accuracy and reliability. You have to know this for every single practical question, so it's worth knowing. Accuracy is basic. Oh, a mass balance is just something which you weigh your food on. Well, weigh is the wrong word, but I'm just using it to make sense. Let me show you on the computer. Wait 1 sec. Where on earth is? Oh, here we go. It's pretty much this. Just a scale, yeah. All right, so for accuracy, depends on the equipment you're using. Like for instance, if you want to measure time and you use a stopwatch, that is not that bad. But imagine you guys use like light gates or something automated. That's a lot better. Whereas reliability is basically repeating the experiment. Yeah, so you just have to repeat your experiment. The more you repeat it, the more reliable the results are. So that's the biggest difference between them two. I think I should open Caboose. I'm pretty sure I'm missing like a ton of stuff, which may or may not come. But I think the bulk of the stuff which I've done now should be coming because they come up in pretty much every single year. There's certain questions that they just have to bring because it assesses your learning for so many different points. Let me think. In terms of circuits, just trying to think what else is there. That is in combined, and if we finish combined, we can go to triple. Bear with me. I'm just opening the book quickly just to see. Before your exam tomorrow, just try to write all the formulae out. That's probably the best thing you can do rather than trying to read over so many stuff. Oh, is forces going to come up in paper 1? Are you sure? Pretty sure paper forces was paper 2, no? Ionization. Did I? Wait, ionization. Oh, yeah, to do with radiation. Yeah, I'll explain that right now. Let me just quickly. That's strange because Mr. Ali said that for triple they all have to be paper one. Well, at least for physics they will be. So I can assure you that. Because that's what they're doing. Oh, okay, mixed them. Wow. Or maybe you guys finished everything. But I mean, well, my condolences, okay, but that means you guys got quite a bit of stuff. Um, okay, so for paper one combined, oh yeah, there's one last thing, but you guys pretty much know this already. But that's just to do with the structure of the atom, which I don't think I need to go over that much. Aha, specific heat capacity, I almost forgot. Yeah, here we go. So you guys need to know these two, specific heat capacity and specific latent heat. Because they could potentially give you like I don't know 6 mark on this. So you guys need to know the definition for both of them. I think they give you the formula for SHC and SLH, so they're quite easy. For SHC, you guys just need if I give you 1 kg of a substance, let's say it's anything like iron or something, what happens is the SHC is defined as this: the energy required to raise the temperature of 1 kg by 1 degree Celsius. So if I had this 1 kg of material and I fed it energy, by the time its temperature increased by 1 degree, the energy is SHC. So if you guys want a formula for this, it kind of looks like this. So energy is equal to, or say energy transferred to be very specific. So energy transferred is equal to SHC multiplied by mass of the object multiplied by the change in temperature. But like I said, guys, make sure that this is like secondary revision because, I mean, well, I know specifically for combined because this came up for combined quite often, so I don't know if they'll bring it again for combined. For triple, I'm not too sure. But do this only after you do electricity and radioactivity. So energy transferred is SHC times mass times change in temperature. So SLH is the opposite. SLH is pretty much energy transferred is equal to mass times specific latent heat. And I'll explain them both using a graph. There's one graph that can explain everything. So it's pretty much like this. What you guys need to know is it looks like this. 1, 2. And then you have time. And you have temp as well. Oh, I'll explain it now, Chicardi, don't worry. Just draw this graph and I'll explain everything. So say you have an ice cube right now. This ice cube, you start here. So this phase here is a solid. So this whole line's a solid. Oh, what it stands for? Okay, it stands for specific latent heat. Yeah, you know, the reason why this graph is so important is because this graph alone explains the entire P6 pretty much. So yeah. So what you guys need to know is that a solid is there. That means this one's a liquid. And then this one is a gas. So you have to know these three. Now, you guys might be wondering what's happening over here and over here. Yeah, it should be, yeah. I think pretty much everything which is in combined has to be in triple. So unfortunately, you guys cannot escape from that. Unless Mr. Ali said otherwise, but that would be strange because P6. Oh, do you guys not have SLH and SHC in triple? Okay. So temperature and time. Oh, that makes sense. But for combined, it's used in 2018 papers. So solid, liquid, gas. What you guys need to understand is when you heat up or when you feed energy to a solid, it basically melts it. So this represents melting. And then here, it will be boiling or evaporating. So you guys have to know these two. So here's where your state changes from there and changes there. And these are the actual states. So based on this graph, you guys have to come up with two conclusions. One thing is that energy can only do two things, and they cannot do them together at the same time. It can either raise your temperature, so it can either raise your temperature, or it can change state. It cannot do these two at the same time based on the graph. And you guys can see, look, right here, you're still a solid all the way till there, and all it's doing is just remaining a solid, but the temperature is going up. When it starts to melt and become a liquid, the temperature is fixed, it's not going up. So it either does one or the other. You guys have to know this, yeah? So raise your temperature or change the state. Oh yeah, whoops, I forgot to put the units. My bad. Yeah, so seconds and then degrees Celsius. Whenever you guys plot a graph, just make sure your units are always on there. Otherwise, you lose easy marks. Okay, so everyone pretty much should have this written down or drawn at least. Okay, now the thing is, I'll just do one question and we'll just move on to something else. For SHC, they might tell you SHC of water is 4,200 in the question. They'll tell you the change in temperature is 42 degrees Celsius, and then they'll tell you the mass of the object, which is undergoing change, is like 40 kg, right? And they might tell you what's the energy supplied. So all you do is you just use the formula as shown here. You're trying to find energy, you have all these three, just turn them together. So all you're going to do is you're going to do this, multiply by this, multiply by that, and you get your energy. It's just that simple. The worst they can do is just rearrange it or give you it in grams. So just watch out. You always want it in kg. Yeah, you don't want it in grams. So the formula will just be energy is equal to mass times change in temperature. This triangle just means change in, I think it's Greek, I don't know what language, whatever. So change in temperature, and then you times it by specific heat capacity. And then you end up with 4,200 times 42 times 40, which gives you a number. But that number is the answer, pretty much, yeah? So that's how you guys do it. What else is there? Conduction, convection. There is renewable, non-renewable energy. I don't know how you guys are with that. I've seen one or two instances where they give you 6 markers and they tell you discuss the advantages and disadvantages of like geothermal or hydroelectric or tidal. So just let me know if you guys want me to do that. Because I think as far as all the main concepts, we've pretty much went through the most likely things in the exam. Okay, I'll go through it then. I'll give you. I'll go through. Yeah, I'll explain it now. Solar and wind are probably the easiest ones. So I think we'll go through all of them. So solar energy, we just know that you use either solar cells or solar panels. So say this is like a solar panel there. What you guys do is you use energy from the sun to generate electricity. So the advantages is quite simple, is that no pollution emitted. So no pollution, and it's also renewable, right? So it's not going to run out. Those are probably the two easiest advantages ever. Disadvantages for solar is going to be quite expensive to set up. It's definitely not cheap. And then you could say maybe not reliable, because think about it, not reliable depending on country. Because if you guys are in the UK, we all know how our weather is. It's not always sunny, so it's not always going to work for us, is it? So not reliable depending on location, I guess. So solar is pretty easy, yeah? No pollution, renewable, quite expensive to set up, and not reliable depending on location. Now, moving on to wind, because wind is super easy. Wind energy, yeah. So wind, the good thing about wind is that it's has the same advantages as don't worry, the grade boundaries are low. You need like what, 15% to get like an A or something. So what you guys see here is that the advantages for both wind and solar is the same. They both emit no pollution. Well, the thing is to make wind turbines, there is a bit, but what you can say is um overall, so what you guys need to mention is just what? Overall, very little pollution emitted. And it's also renewable, so that's pretty easy. Okay, now disadvantages once again is not reliable. You guys know it's not always windy. And it's an eyesore. Like think about it. Imagine you had a massive wind turbine right next to your house. That will ruin the scenery, it'll ruin the landscape. So you can actually say the word eyesore and they give you a grade for that. So it's up to you. Or you can say ruined scenery. So yeah, not reliable, eyesore. What else is there? Quite expensive to set up as well. Not very efficient. Yeah, so there's quite a few things as well, yeah. Oh no, I'm joking, I'm joking. You wish it was 15. But anyway, so 1, 2, 3, 4, 5. But I heard that to get a grade 7 was about 50, yeah. 50%. So it's not that bad. So you guys have to know this. All right, now we finished with the easy stuff. Let's go into the actual stuff that might come up. Now we're looking at hydroelectric, so keep your eyes peeled for this. Because I don't know, this just seems like one of those things that no one really gets. But for you to get hydroelectric, you have to utilize gravitational potential energy. So say you are somewhere very high. This is where my drawing will actually hinder you guys understanding what I'm about to show. Say you're somewhere very, very high, right? And you have like a dam filled with water. So this is certain height, and there's the ground. We can say the ground is there. And you have certain turbines like that. What you guys need to understand is that what you guys need to understand is that pretty much when the water starts to flow down, we all know that gravitational potential energy is converted to kinetic energy here, and that's what kind of causes it to transfer to the turbine. So what you need to mention is that water is stored in a dam at an elevation. So let me just actually write it. So water stored at an elevated level. It's very important to elevate, otherwise it doesn't work. And then water is released. No, wind turbines are the easiest, Eve. You should be happy if it comes up. Water is released. And the thing is, when water is released, what you need to mention is that GPE converted to kinetic energy, transferred to the turbines. When it hits the turbines and the turbines spin, and you don't need to say the rest, don't worry about it. So transferred to turbines. You're all doing physics for A level. I don't know what you guys are talking about, but yeah. Oh no, no, Chicardi. I'm just basically explaining how it works. So, because if you don't know how it works, it's very hard to talk about advantages. So, elevated height, you release the water. Its GP is converted to kinetic energy. It basically slams into the wind turbines. The wind turbines start to move, and you can generate electricity. Basically, yeah. Obviously, there's more stuff, but you don't need to know that bit. So you have this, and then what you guys do is now let's do advantages and disadvantages. So advantages is let me think on which ones I can give. So I might do advantages and disadvantages as well. Wait, which one should I start with? Okay, so let's say no, actually I'll start with the negatives. We'll just say that can cause floods. The thing is, if the water is not controlled, what happens is you can actually flood an area, which is quite bad. We can say that it is Renewable, so renewable is useful, which is an advantage. No pollution. Or we can actually, let's be very specific, very little pollution, because there have been cases where there is some pollution. So renewable, very little pollution can cause floods, and very expensive to set up, yeah. So if you guys think about it, it's not that different from other sources. So very expensive to set up initially. But I think if they want you to explain how it works, then you guys are in heaps of trouble. But now you are not because you guys know how it works, yeah? So advantage is just renewable, very little pollution. And then disadvantages can cause floods and very expensive to set up. So that's what you guys need to know for hydroelectric power. Hydroelectric power. Okay, I think I shall just do one more topic and then call it a day because I feel like I've done an arm workout holding this camera for an hour and a bit. So one, two, let me see, 1, 2, 3. All right, we finished this. What next? Let me see. All right. P8. Wait, let me see which one is it. 8 to 16. I need to track the triple. Where is it? Yeah, I should do, but you know. Hmm. Series circuits parallel. All right, one last thing in electricity before I forget. How can I forget this quickly? This is like the most important thing in electricity. So you have a parallel circuit. Yeah, I don't know how it slipped my mind. So say you have a parallel circuit with three branches like this. You have an ammeter there. You have an ammeter there. You have another one here. And then you have one here as well. So what you guys need to know is that say this is A1, A2, A3, A4. You guys need to understand that if all these light bulbs are identical, what that means is that your current, let's say initially it was 6 amps, right? When your current reaches this point there, it's going to split between there, there, and there as well. So ideally what you guys need to understand is that because they're all identical, you just divide this by 3. So it's going to be, yeah, pretty much 2 amps, 2 amps, 2 amps. Because they could give you this in the exam. They might ask you just to fill in numbers. And then they might give you another one there. But then you guys need to know by the time they all come back again here, they all add up to what you started with. So once again, here's going to be 6 amps there. So ideally what you guys need to know is that 6 amps and 6 amps before and after the separation. But then what you guys have is in between, it kind of splits up. Okay, let me explain why a voltmeter has to go in parallel. So let's say you have a resistor like this, or a light bulb, doesn't really matter, and then you have a voltmeter like this. What you guys need to understand is this: voltmeters have infinite resistance. So because they have infinite resistance, think about it like this, right? Because they have infinite resistance, if an electron was moving here, it wouldn't dare go this way because there's infinite resistance waiting for it there. So every single electron will just go straight through the resistor which you want, and nothing will be diverted to the voltmeter. So the voltmeter does not disrupt the flow of electrons in a circuit. Whereas if you put it in series, shout out. Yeah, but there's only Road and Valley peeps here. I mean, you know, there's no one external watching. But yeah, hey, hello. Yeah, I don't know. Okay. No, I'll do it in another video which I actually upload, I guess. But you see here, so the point is, if you put it in series, say you put voltmeter in series, because it has infinite resistance, nothing will be able to get through this, and this resistor will have no current going through it. It just acts as a massive blockade, and you'll have zero current in the entire circuit, pretty much. So you have to put it in parallel to make sure that no electrons go through it, whereas they still go through the rest of the circuit, if that makes sense. So just that, but really and truly, you only need to know that for A level if you plan to do it. So don't worry about it for now, I'd say. But yeah, they have infinite resistance. Okay, but I hope this bit makes sense because you all need to know this. And the formula to find resistance in parallel, before we forget, is okay. Now it looks like a fuse. Just imagine the resistors, guys. So the resistors. Let's say I gave you 20 ohms, 20 ohms, and 20 ohms, right? If you want to find the total resistance in parallel, you guys have to use this formula here. It's basically 1 over R total. So your total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, blah, blah, blah. Now, the thing is, all you do is just replace all these with those numbers there. So it'll be 1 over 20 plus 1 over 20 plus 1 over 20 equals 1 over R total. You guys can use a calculator. When you add all of these up together, it gives you 3 out of 20. Gives you 1 over R total. Now comes the tricky bit. You do not want your answer to be 1 over your R total. In the question, they'll ask you, what is R total by itself, not 1 over it. So in maths, if you just want to find the denominator, you need to find the reciprocal. So you do that to the other side as well. So RT will basically be the opposite, which is 20 over 3, which is about 6.6 recurrent or something like that. Yeah, so you guys have to know that. So once again, resistors in parallel, when there's more than one loop, you just use this formula here. You might want to write this down because they will not give you this. I'm like, I don't know, 80% sure. Okay. Now, yeah, alternating power, and I don't think that's going to come up. You guys can read some extra stuff on electricity, but I'm pretty sure majority of the stuff is pure circuits like this, thermistor questions, like so. So this is really advanced one. They could ask you that, or they can ask you graph profiles as well. So the thing, oh, which book to use? No, I mean the Caboodle book. Yeah, because if a voltmeter had zero resistance, every single electron will go through it, and the voltmeter will just catch on fire, and it will just it will just get destroyed. Yeah, but the thing is, you want them to go through the resistor, as in, because think about it like this, guys. You use a resistor in a circuit to pretty much regulate the current. If the current gets too high, you will cause fire in the circuit. So yeah. All right, I'm running out of paper. What the hell? All right, here we go. Let me see. What time is it? It's 8:16. I think probably what is best is I should just make some questions and then just put and show my homework quickly for you guys to try. Because otherwise, yeah, otherwise, I mean, it'll be too much for you guys to take in. But before I stop, wait, let me just do one last triple topic. What was it? It was it space? Do, 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 do. All right. Um, what Road and Valley Fan TV? Okay, in terms of, let me think. All right. So yeah, space. I mean, I'm kind of rusty at it, but let's try. Okay, so for space, what you guys need to know is, all right, anyone who's doing combined, just be on the lookout for a worksheet in like about 20 minutes or 15 minutes. All right, so imagine in space, you have, I can't remember this word. Let me see. So you have, oh yeah, you meant to talk about life cycle and stuff. Yeah, it's only in triple. Let me think, let me think, let me think. Okay, yeah, I remember it. Yeah, I remember now. Okay, so you basically start with, or actually, you know what, guys? Triple guys, give me just 1 minute. Let me just quickly check in Caboodle. I just need to quickly, because yeah, I haven't told this in like forever. But wait, one, two. Yeah. Let's see. All right, triple. All right, take care. All right, let me see. Stars. All right, got it right now. Yeah. So what you guys need to understand is after the Big Bang, you pretty much had large clouds of like dust and gas. So just say, imagine this is like the universe there. You pretty much just had like clouds of dust and gas everywhere. And basically, what you guys need to know is anything with mass, even though they're very, well, not that heavy, I guess, compared to other stuff, but anything with mass has its own like gravitational field around it. So everything was pretty much attracting each other. So you guys need to know that due to the pull of gravity, these masses of dust and clouds pretty much get attracted towards each other. So the first thing is gravity pulls in clouds of dust. Now, what we know is whenever you have a force and it's basically pushing or pulling stuff in a certain direction, there is work being done. So if you guys look here, work done is equal to force times distance. So because there's work being done, what we can say is the temperature will rise. So as everything's getting clumped, so as what can we say? As dust gets clumped together, the temperature rises. And what we know is, guys, that you need a lot of temperature for for nuclear fusion to happen. Oh, how do you work out the age of the universe? Is that in your spec? Because if I mean, I remember we done something to do with an A level, but I just forgot everything. I'll be completely honest. I don't know if it's in your spec, but all I can remember from Age of the Universe, I know. Let me think. Isn't it using absorption and emission spectra, and then I'll have to look at it again. I'm so rusty at this topic. It's like my worst one so far. Yeah. Rest in peace. So gravity pulls in clouds of dust. Yeah, okay. I guess I'll have a look at it quickly. But yeah, after let me just explain how the life cycle for star, then I'll start this. All right, peace. So gravity pulls in clouds of dust. Work is being done. They'll be really happy if you come up with this answer. 'Cause this is for like year 13, but work done. means that there's temperature rise in temperature. And then what happens is fusion happens. So when nuclear fusion happens, we know that you start with the most basic element, which is hydrogen. When you keep clumping hydrogen, eventually you get what? You get helium, and then you keep getting heavier and heavier and heavier elements. Whether you guys need to know this for GCSE or not, but basically they keep fusing together until they make iron, because iron is the most stable element. So what happens is you start with the smallest element, keeps going higher and higher and higher in mass until it becomes iron. Now what we need to know is that imagine this is your star right now, right? So this is your let me think, proto star. All right, so let's imagine you just have your star. So this is your core actually, where nuclear reactions are taking place. You guys need to understand it in terms of force inwards and outward force as well. So the force that's trying to crush this is due to gravity, and then the outward force is due to the energy released due to nuclear fusion. Pretty much, that's what you need to do. So gravity is trying to crush it, energy from nuclear fusion is trying to expand it. Now, what we know is by the time you start reaching super heavy elements close to iron, well, they're not that big, but they're pretty big. So by the time you start reaching those, this actually starts to swell up. So you start to get a red giant, yeah, and then you pretty much eventually reach your stable phase. So what happens is, what's it? You get a red giant, and there's some expansion going on. So expansion going on. But the thing is, when all your reactions pretty much get stopped, so let's basically say you've managed to reach iron, you run out of ammo, there's no more hydrogen to kind of convert into other elements. What will happen is there's no more energy being, or not as much energy being emitted. So what happens is the pull of gravity pretty much crushes the red giant, and then eventually what will happen is you will end up turning into a white dwarf. So I think in terms of forces, it just makes sense that when your reactions finish, when there's no more nuclear reactions, there's no outward force, so therefore gravity just crushes you. You turn into a white dwarf. And the reason why it becomes white is because it starts to cool down. So it cools down dramatically. And that's pretty much what happens, yeah. Um, yeah, apologies. I mean, space is just super weird. If you guys want to know red and blue shift, I still know that if you guys need to. But it's not that hard. You can use like the ambulance analogy for that. All right, let me show you red and blue shift quickly. Red and blue shift is basically, say you have an ambulance here, and then say someone is standing there, right? Think about it like this. When the ambulance approaches you, the what can we say? So the intensity increases. So you can imagine when the ambulance approaches you, the intensity increases, but as it gets further and further and further away, it kind of becomes more and more and more faint. So similarly, what we can say is, um, so you can say redshift is basically when ambulance moves away from you, and I'll tell you how it makes sense when you look at the EM spectrum, because moves away. For the EM spectrum, I think especially for you triple guys and girls, you guys need to know that you have radio, micro, infrared, visible. What else do you have? You have ultraviolet, X-rays, and then gamma rays. The thing is, you see here, infrared carries less energy than UV. And we know that blue is somewhere there. So naturally, when something is shifting away from you, there's less and less energy being transferred to you, and therefore it's called redshift. Blue shift is basically when something approaches you. or when it's basically has motion relative to you that's incoming. So basically, when the ambulance is coming closer and closer and closer to you, you actually hear it more and more. The intensity increases because it carries more energy. That's all it is really. That's the basics behind it. But do you guys do emission and absorption spectra? Because if it sounds a bit confusing, just as a last ditch effort, because it's a bit too late now to kind of go through all of it, but just to save you or just to barely nab a few marks, just you can do it like this, right? Red shift, blue shift. You just mentioned that red carries less energy, and then this carries more energy. And the only way you can remember this is basically, yeah, with the black bars, yeah, carries less energy and carries more energy. And you guys just have to remember this in terms of the EM spectrum, as in like you got red there, and then you got violet there. Blue's closer to violet, somewhere there. So you guys just have to understand that this is more energy, this is less energy. Blue shift is when something comes closer to you because it's louder. Louder means there's more energy. So yeah, so the time when the ambulance is the loudest is when it's closest to you, and therefore that's blue shift. When it's furthest away from you, it carries the least energy because it's the faintest. That's all you need to know. Oh, you guys are talking about emission and absorption. Let me check in your book how much you guys need to know. Okay, what I'll do, I'll give you guys one example using the book. So you see here from your in your Caboodle book, um, what I want you guys to see is this because I can't all the different colors, but let's say that you know a star is emitting hydrogen at any one point in time, right? Now, what you guys do is you get your own source of hydrogen from a lab and you fire it and you kind of get a profile for it. This profile basically shows you exactly what colors electrons. So wait, actually that's A level. I don't want to confuse you. This basically shows you what hydrogen on Earth the profile looks for it. Now what you're going to do is you're going to now get some hydrogen samples from, let's say, via light coming from a different galaxy. And if you guys notice here, these lines have been shifted more towards the red side. Now what we said is, and let me just make it clear once again, is that if I can find scrap paper. You guys need to know the relationship between wavelength and energy. So wavelength and energy are inverse. So as your wavelength increases, your energy decreases, and as your wavelength decreases, your energy increases. So which kind of makes sense because if you guys look at gamma, if you take a step back and look at a gamma wave, gamma has very, very short wavelength, but has incredible amounts of energy that it can transfer. So similarly here, I want you guys just to understand. So let's look at redshift. We know that it has a very, very long wavelength, and therefore it carries very little energy. Just talk about red, like ray of light, and then low energy. Blue shift, I do not have a blue pen, so this is not ideal, but whatever. Okay, actually I can use, no, never. So just imagine this is blue shift here. Blue shift is the opposite of red shift. It has a short wavelength and it carries a lot of energy. So all we're trying to say is when you have a profile like this, you don't need to understand what these lines mean. All they are is just that hydrogen electrons absorb these, but is of no relevance right now. So let's just say this is hydrogen on Earth. And then I will draw hydrogen, let's say on somewhere very far. Let's just say Jupiter. It doesn't really matter. I'm just hypothetically saying this. What you guys should notice, because Jupiter's much further away from us, this is the red side, this is the blue side. Because Jupiter's much further away from us, we know that the wavelengths will be much longer because it's stretching out, right? So all the lines will start going a lot closer to the red side. It'll look something like this. So if you compare this with this, look, this line has gone more to the red side, more to the red side, like that. But on the flip side, let's now say that we're going to compare it to something which is actually closer. So let's say that you have, let's say you have the same hydrogen sample from Mars, maybe. So it looks like this, like this, like this, like this. And then now let's say we're going to look at it on Earth, right? On Earth, what you should notice is because Earth is obviously we're on Earth, which is closer than Mars, everything should actually be what? Blue shifted. Actually should be much closer. So it might look something like this. So all you guys need to understand is that redshift and blue shift just kind of present or allow us to understand how things are moving relative to us. So if they're moving closer to us or further away from us. Yeah, so one last thing, redshift is moving away from us relative to us. And then blue shift is moving closer. So that's what you guys need to understand. So over time, this is how they can kind of tell whether a comet or a meteor will strike us after several hundred years, because what they might do is every few years they'll take a reading of this, and what you might notice is it creeps ever closer to the blue side. So that means it's coming closer and closer and closer. So that's what happens. Don't know if that made sense, but that is the best I can think without making it too confusing. Because if I added electrons and stuff, that's unnecessary for GCSE. Yeah. All right. Was there any other topics for triple other than space? Because I hate this topic. All right, guys. Yeah. Okay. Yeah. I think. Yeah. I'm done as well. I'm fatigued. So, no worries. If you guys need help, I'll be there in the morning anyways at school. But yeah, best of luck, guys, for your exam. All right. Take care, guys. Bye.